So we start part 4 with an introduction that just gives us some definitions and tells us about some different ways that we could calculate probabilities. So probabilities are the likelihood or odds of a random phenomenon occurring. And really, I don't like this definition. The random phenomenon itself is going to occur. It's an outcome for a random, an outcome for odds. Yeah, this is a terrible definition. Let's fix this. Let's fix this right now. For a particular, particular outcome of a random phenomenon occurring. There we go. That makes that definition slightly better. So we've got some definitions within that right there. We've got outcome, which is what happens at the end of a random event. And then we've got some other ways that we can talk about these random phenomena, namely trials or experiments. So the piece that really matters here of all of this are how we define events and how we define probabilities. So if our random phenomenon or our trial is flipping a coin, we could write a whole question out and say, what's the probability of that coin flip resulting in heads? And that's a big sentence. That's fine, but mathematicians, statisticians, we're all pretty lazy, and so we do a lot of things shorthand. So what we'd normally do is instead is we'd say, okay, let's just say that H is that the coin comes up heads. And then instead of writing out the whole sentence, we can just say the probability of heads, that's the probability, or the probability of H, that's the probability of us getting heads. So that would be 1/2. So just throwing out those because we're going to use those quite a bit, defining our events and then using this probability notation. I do want to talk to you really quickly about a pet peeve of mine. What I have students do a lot is that they'll put the actual probability inside of that P in parentheses. This doesn't make any sense. This right here says the probability of H. So if you've seen function notation before, right, this is the function of X. Like this is the probability of this thing happening. It doesn't make sense to throw the actual probability in there. That should be after the equal sign. So that's just a pet peeve of mine. I don't usually dock points for doing that, but still, please don't. Make me happy. So that third bullet point talks about the set of all possible outcomes being called the sample space. So if you're rolling 2 dice, the sample space for all possible outcomes is given here in exercise 1. Now, one thing that you can do if you wanted to get a little mathier here is that we could write down that S is equal to, and we could use the big set notation to say here is the set of all possible outcomes. If we had the set of all possible outcomes, probabilities are frankly easy to find. But we're going to start first by actually defining some events. So our first event here is event A is rolling 2 dice whose values sum to 7. And all it asks here is what are the outcomes contained in A. So now we're just going to go ahead. If you've played craps before, you probably know the things that sum to 7. But we've got 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. Those are all the outcomes in our sample space where our 2 dice sum to a total of 7. Boom. Oops. So again, we'll use a little set notation to say, hey, here is everything that makes A true. Here are all the outcomes that would be in event A. So you guys can take a moment and do this for the next 2 events. So if you did this, the next event B is about rolling doubles. So now we're doing the opposite diagonal, right? 6, 6, 5, 5, 4, 4, so forth. So 3, 3, 4, 4, 5, 5, 6, 6. Those are our different doubles. And then C is summing to 10, which is the smallest event space that we'll have because we only have 3 ways to do that. 4, 6, 5, 5, and 6, 4. I keep trying to make 6, the parenthesis into the 6. All right, so that's event spaces and sample spaces. Fairly straightforward, just writing out all the different things that are the result we care about. All right, so types of probability. We have three that we're going to talk about, one that we're focusing on in part 4. So the first one is classic probability. This is the equal likelihoods approach. So in these cases, we're dealing with outcomes that are equally likely. So if that's true, if everything in your sample space is equally likely to occur, then we can use this classic approach, and you're just looking at the number of things in the event space A versus the number of things in the sample space. That's it. So this is what we've probably seen the most in terms of probability. It's what this entire section is about. So as we move on, it basically asks us, is the classic approach something we can use for the dice rolling example? And the answer here is yes, definitely. Every single outcome, when we look at each of these rolls of the dice, a pair of 6s is just as likely as a 5-4. Everything here has the same exact likelihood because we're just rolling 2 dice, and the 2 dice don't influence each other. So we've got equal likelihoods. All 36 outcomes are equally likely. So I had students in one of my 119Xs that were like, no, it's not. But they were busy sort of thinking about all the things that you might do in craps, right? Like summing to 7 is not the same as summing to 11 or 10, those events we talked about before. For this particular one, we're just talking about each of the items in the sample space. Are they equally likely? And in this case, the 5-6 and the 6-5 are distinct, unique events, so they are equally likely. All right, and so if that's the case, we can then find our probability of A. This is just the number of things in our A space, and there were 6 of those, over the number of things in the sample space. We could do the same thing for B. Again, we could count up. We could go up to here to B and go 1, 2, 3, 4, 5. There's 6 different things in B out of our 36 different options in our sample space. And for C, well, there were 3 ways to sum to 10 out of 36. So that's the classic approach. That's what our focus is for part 4. All right, the next approach, this is what a lot of our statistics are based on as we move forward in the class, is empirical probability. We call this frequentist probabilities. There's frequentist and Bayesian statistics, and this class focuses on frequentist statistics. So frequentist statistics, or empirical probabilities, are based on what would happen in the long run. So let's say we're playing a game like Pass the Pigs, which if you haven't played it is a game where you literally throw little pig dice. If you're throwing pig dice, there's a bunch of different ways that they can land. So just to show you, you have the ability for pigs to land on their nose and ear, on their snout alone with their front legs, on their sides, if they're touching, you get it on their back, on their feet, and you can see there are different points associated with each of those things. Now, a mistake would be to say the probability of getting the pig to land on its feet, to get a hoofer, is the same as the probability of getting a jowler, right? The one where it's landing kind of on its cheek. Because that assumes that they're all equally likely. You could look and say, well, it can land on its back, side, and it has 2 sides. So there's back, side 1, side 2, feet, nose, the snouter, and then the leaning jowler, which is the nose and the ear. Those are pretty much all the ways it could land. So if you were still using the classic approach, you'd say there's a 1 in 6 shot for any of those. But that's not true, right? That's why there are different points associated with them. So a way to figure out what those probabilities might be would be to use the empirical approach. And that would be that you just roll the pig a bunch of times and see what happens, right? So if I roll the pig 100 times, and of those times on its feet only happens 10, then I'd say there were 10 out of 100, that there's a 10% chance of this occurring. So that's frequentist. This all relies on the law of large numbers. The law of large numbers tells us that if we take and do something a really long time, we take a really large sample size, that will eventually approach the real value. So you got this cute little applet here showing you basically the empirical probability of flipping a coin and getting heads. So after one coin flip, the empirical probability says, oh, we got heads out of one time. That's a 100% chance of getting heads on this coin. So that's what we got there. Looks like they flipped again, and this time they got tails. So now we have a 1 in 2 shot. It's 50%. But looks like they got heads again. So now we're at a 2 in 3 shot. So it keeps going, and eventually it starts leveling off as our sample size gets large enough, right, as we do this enough times. And this is what we leverage in inferential statistics later in the course. And then our last type of probability is super lame, but it's another type of probability, and that is a subjective approach. So just using the information that you have available to you and your opinions to come up with probabilities. So obviously not the best method, but an idea of something that might have a subjective probability would be something like your belief on what the probability is that the Chargers will make the playoffs. So you're obviously bringing some of your own bias into this, whether you're a Chargers fan or not, but you're also bringing in a lot of information that you may or may not know, right? If you realize Hunter Henry just got injured, gone, I don't know, something happened to our tight end, then that might lessen the probability of what you thought previously. Or you might look at the other teams in our division and decide, well, since at least one team is going to go through, I think the probability is going to be this. You're not going to use the classic approach, right? You're not going to say it's a 1 in 4 shot, because that would assume every team is equally likely to make the playoffs. But you are going to use what information is available to you to assign a probability to that.